jump into doing a little bit of a reset on DC. Maybe I'll explain it a little bit differently than what you had. For those of you that haven't had DC in quite a while, to just make sure everybody's sort of up to speed on that. You know, we'll see where we're at. If we still have some time for lecture, we'll start diving into AC theory. Otherwise, we'll jump into lab. I know you guys don't like math, but we can get through this pretty quick. So I know you guys remember there are various different counting systems. You might remember the Roman system. Every time you look at a dollar bill, there's a few Roman numerals there. The system we use is called Hindu-Arabic. There are 10 symbols, 0 through 9. The Chinese use some really bizarre system. I stared at this one for a while trying to figure out how it works. I couldn't do it. So they have all kinds of symbols. The Greeks, one of the things the Greeks did, they also used a derivation of the Arabic symbols, but they figured out that you couldn't calculate pi. You couldn't actually get an accurate dimension for, or a number for the value of the ratio between the diameter of the circle and the circumference of the circle. So for all their architectural work, they measured based upon that ratio. So they actually measured in turns around a rod. In any circular component, that automatically compensated for the value of pi. Now, probably didn't make a big deal on smaller things, but when they made a much larger, like a big circle that maybe was sort of all the way around a stadium or something like that, so they knew that it couldn't be calculated, so they used something that was a circular object as the measurement system. And then they would, by using that, they knew how many spans the circular area was versus the diameter, but didn't actually have to calculate any value of pi. Okay, then you remember there's a whole bunch of different kinds of numbers. If we say it's a real number, we're talking about any possible number. Okay, now I don't know why they needed the word real. It could have been just a number, right? I suppose it differentiates from other things. If it's a counting number, a number that has no fractional component, we'll typically use the word integer, whole, or natural. I think natural can be a positive or negative or zero. Fractional values can use either a 0 and a fractional value or any other integer and a fractional value. And that fractional value can be written in a variety of different ways. Then all of those are somewhat rational numbers, you know, in here and there. There are also some irrational numbers, meaning they're numbers that there's no way to figure out what it actually is. So the square root of 2. You start taking and working out what number is times itself will be multiplied and come up with 2. It'll be a never-ending decimal, random decimal value. Same thing true with the ratio of a circle, diameter to the circumference of the circle, or pi. 3.1401, blah, 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 it just goes on. And, you know, I'm sure there are people that have calculated it out until they dropped over dead at 95. The square root of 1 is another one. What number times itself equals -1?
Nothing.
And the truth of it is the square root of any negative number, right? What number times itself equals another negative number? Now, one of the reasons we use the square root of -1 algebraically, we actually create a symbol for it, is if we end up with a negative number that we then have to do some square root function on it, we can extract mathematically the -1 value out of it, and then hope later on in the problem that both sides cancel the -1 out, in which case I don't have to solve it, right? So we keep the concept in mind as an irrational value that if we can cancel it out of the math later, yippee-yi-yay, we don't need to know it. Okay, so then you guys remember the counting systems. for normal math, we use the base 10 system. So you start at the first symbol, 0, count all the way up to the 10th symbol, 9, and then you run out of symbols. So you've got to go over a decimal place and start with a new symbol. Now, in truth, we sort of presume there was a 0 there. So once we get to the next value, this started out as 0, went 0, 0, 0, 1, 0, 2, 0, 3. We can presume it was also zeros, a whole bunch of zeros. This is now, this stepped up to 1, up to 19, 2, 3, and all the way up to then needing 3 decimal places, where you presume there was a 0 up there, up until you get to 100. Then you move that up to 1. Base 2, we do this in the world of computers, because in any spot for a memory, we can remember an on state or charge state and an off or discharge state. Okay, and we can put a little block there and say, okay, there's an electron charging it or there's no electron charging it. If we take 8 of those little spaces together, we can then come up with a number. You could have an indefinite number, but if we said we have 8 little registers or 8 little slots, we could end up having 256 possible different meanings. Okay? Well, each one of those little slots we call a bit, and all 8 of them combined we call a byte. Remember that? Okay, and then in some of you may remember ASCII, American Symbol Code for Information Interchange or something like that. So for each one of those 256 possible meanings, 0, 1, 0, some combination of that, I think like 32 represents the space. Something represents capital A, capital B, lowercase a, lowercase b, etc., as well as a few symbols. So in the early days, we used a byte to represent 8-bit memory. In later days, we actually allowed for a byte to be 16 bits, which allowed for millions of different possible meanings within each segment of memory slots. So base 2 used a lot of computers. Base 8, you guys might remember from when you were in general. Remember for AN hardware? We broke out dimensions in 1/8 of an inch. So you went from AN2, AN3, AN5, AN6, AN7. There is no AN8, is there, in a bulk dimension? Okay, you go from AN7, once you hit 1 inch, you go to AN10, right? Remember? So that's a base 8 counting system. Going the other direction, past this, when we go to base 16, we're going to need some more symbols. With the Hindu Arabic, we run out of symbols at 9. So what they did is they said, all right, we're going to add A, B, C, D, E, and F. So when you get to F, you're at 15 in base 10. In 16, in base 16, you're at F, right? So it's 0 through F, and then when you get to 16, you put a 10 down, or a 1, 0, and then all the way up to 32, and on and on and on, right? Again, because of the architecture of computers, base 16 language, most computer languages are in base 16 at some level or another. We don't code that anymore. We have computers or computer programs that automatically compile that into some very basic coding like that. But the language that we use will be a plain language, something that's a little bit more English-like. There's a bunch of different computer programming languages out there, but the compiler will then take and convert that into 16-bit language, and then parts of that will be converted into binary, base 2 language, depending on what level of the computer it needs to work in. Okay. You guys remember all that. Then you remember all the operators, right? Most of these are pretty straightforward. A couple that you may not have used too often. One of them that's kind of useful are these guys right here, plus or minus or equal to less than. Plus or minus is very common in specifications. Typically, they'll say like 0.250 plus or minus 10 thousandths. So what they're saying is it can range from 0.250 up 10 thousandths, or 0.260, or down to 0.240, right? You go up or down within that range. Unfortunately, some manuals, I don't know why they do this, they'll bracket the other side. So they'll say it's 0.240 plus 20. They won't put the plus or minus. They're just saying plus, so it can go from 0.240 up to 0.260. So there are a few manuals that do it that way. That's a little confusing. If you're looking at the spec, you'll see the plus symbol and kind of, what does that mean? Whereas usually when you see the plus or minus, it's pretty easy to recognize, oh, that's a tolerance, that's a range that it can be in. Another thing to note is the vinculum. The vinculum can act like parentheses in that it can change the order of operations. We'll talk about that in the next slide. But so let's say the vinculum is the line that goes over a division or the square root symbol. So let's say I have 9 plus 7. In order of operations, I'd solve for the square root and then add it to 7, right? We get into the order of operations. But if the vinculum comes all the way out to there, now I would take the 9 plus 7 and derive the square root of it, right? You guys remember that? So depending on how long that little line goes, it's called the vinculum. I don't know who came up with that. All right, and then order of operations, you guys remember PEDMA, or please excuse my dear Aunt Sally. This one, probably the only caveat to remember is that within the group of multiplication and division, left or right takes precedence. And within the group of addition and subtraction, left and right takes precedence. So let's say I take 7 plus 3 minus 9 divided by 3 times 2. So if you didn't have the left or right, we'd do the multiplication, then we'd do the division, then we'd do the addition, then we'd do the subtraction. Okay? If we just followed the straight order of operations. What we will do instead is, within the group of multiplication and division, we'll go left to right. Then within the group of addition and subtraction, we'll go left to right. So what would happen here is we take the 9, divide it by 3, multiply it by 2, right? Set that aside. We would then add the 7 plus 3 and then subtract this from it. Right? You guys remember all that? Okay. Where I tend to get messed up is when you've got a whole bunch of addition, subtraction, division all together. Sometimes then you plug it into your calculator. Sometimes like, wait a minute, I gotta write that out. Make sure I remember it. Okay. This one can sort of get confusing in a variety of different ways. Much of this we can remember. The commutative property is where in addition and multiplication things can be swapped back and forth. It doesn't change it. You can't do that in division and subtraction. The associative property somewhat says the same thing. I can do this first and that, or that first and that, with addition and multiplication. Distributive says if I have parentheses, that's the same as multiplying this by this individually and that individually, then adding them together. Again, only works multiplication and addition. The identity property really works with respect to 0 and 1. So 0 in addition doesn't change the value of it, and multiplication times 1 doesn't change the value of it. The inverse property, in addition, will ultimately cancel the value. In multiplication, the inverse, which is really a fraction, will cancel out the value, leaving you with 1. So anything divided by itself ends up being 1 in every case. Multiplication and division of 0. Anytime you multiply anything by 0, you end up with 0. Anytime you try to divide something by 0, you end up, if you divide 0 into it, you end up with 0. Or if you divide it into 0, you get a 0. But if you try to divide 0 into anything, there's no answer. How many times does 0 go into pie? How many times does 0 go into hot dogs? How many times does it? Doesn't matter what you do, it doesn't make sense, right? Okay. All right. Same thing. The rules of double negatives, that they cancel each other, either in division or the negatives cancel each other. And then lastly, one that's a trick that I often forget is any number can be turned into a fraction. Anytime I want to take a number and turn it into a fraction, all I got to do is put 1 underneath it. I haven't changed the value in it at all. 7 divided by 1 is 7, right? Okay. Anytime I want to take a value and turn it into a fraction, let's say I've got another fraction, I'm trying to figure out how to, smash those two together. Let's say I've got a value of A and it's divided by B over C. Well, one of the properties we've talked about up here is I can flip-flop the equation. I could say A times C over B is the same value. That equals the same value. Flip that over and make it a times problem. Then I can go like that and multiply straight across, right? Makes it a little easier to see. 1 times B is B. A times C is AC. So you do with AC over B. Okay. Now, what the actual value of that is, you don't know, but if you're using A, B, and C to derive or create a formula, once you've done all that, you now have a formula that you can plug any values into. Okay, for the purposes of our work, when I give you problems like series parallel problems, the rounding rule is going to be whatever value you're taking off. You're taking the A off. If it's equal to or greater than 5, you're going to move the 6 to being a 7. If it's less than 5, you're going to leave it as a 6 and just drop the A off, right? And the reason they pick 5 is because you have 5 through 9 is one group of numbers, 0 through 4 is another group of numbers. Okay, that are equal size group of numbers. Okay, so that's pretty standard rule. Sometimes you guys truncate. You just drop it off. If that was the rule, that's okay. You can do it, but we're not doing that. I'm also going to very strongly recommend you guys keep things at least out to 3 decimal places. And if you've got 2 zeros, 0.00, you might keep it at least 3 decimal places past your last 0. Okay? The problem is, if I've got, 9.1234, and I truncate this by rounding it, it's not going to change the value of that number very much, right? But if I'm at the same value, 0.00041, now if I drop the 1 off, I'm going to change the value of this by some relative percentage. And if I was here and I just dropped the value off, I would change it by 100%, right? Okay, or let's say this was 5, right? What would I do if I was rounding to here?
1.
I'd kick that up to 1, and now I've doubled the value, haven't I? the actual value, and change it by 100%. Okay, so whatever your last zero is, carry at least 2 or 3 beyond that. Otherwise, you're going to end up with, it's going to have enough error that by the time I get down to the bottom in those power equations, if that's the way it went, you're going to have numbers that are way, way different. Now, the way I normally do this, when I do the series parallel problems, when I come up with a solution, I never write anything down. I use the calculator's memory. So it's keeping it all the way out to the 12th decimal place. Okay, because in most calculators, at least the calculators I use, have an algebraic array, and I can just keep plugging stuff right back into memory slots. So I'm going to highly encourage you guys to either get used to using that or carry it out a little bit further. Scientific notation, typically not needed unless you have some really bizarre numbers. Get way out into here, it's going to go positive. You're going to say 1.234 blah blah times 10 to the 5. Well, the 5th power is the number of decimal places I went. 1, 2, 3, 4, 5 decimal places. So this value is the same as that times 10 to the 5th. If I'm going the other direction, now in this particular case, I've truncated a fair amount off. Well, truncating, what did we do? 456 off of 123,000, that might be a little bit of a chunk of percentage, right? Depends if I'm building fences, I wouldn't worry about it. If I'm trying to hit Mars, maybe not. Going the other direction, if I have very, very few decimal, it's a very, very small number, many decimal places, I can go this way, 1, 2, 3, 4, 5, 6. Scientific notation, you always take it out to at least one integer, and only one integer. So in that case, I'm going to say I went 6 places, but since I was going this direction, it would be to the negative 6th power. Okay. Probably not going to use this too much. However, what that does is it sets us up for another way of accomplishing this. We came up with these prefixes: mega, tera, kilo, milli. Use those all the time, and we use a lot in electronics. The problem is your calculator has no idea what that means. So if I give you a value in milliamps, you're not going to be able to plug the milli into your calculator. What you're going to have to do is convert it back out of the milli. So instead of saying 1 milliamp, you're going to have to plug in 0.001, right? So make sure you remember to do that. I went and found a cool chart. There's all kinds of, you were pretty familiar with tera now, terabytes, gigabytes, megabytes, kilo, and all the rest of the stuff. Down here, you don't really use deci too much. Centi, you might see centiliter. Millis used a lot. Micro, nano, and pico are also used a lot in capacitor values. Up on this end, we don't really use deca or hecto that much. Kilo is used all the time in linear measurements and weight. Kilogram, kilometer. Mega, giga, and tera are used a lot in talking about computer memory and computer capacity, big numbers. How big is a tera? I'm trying to remember this right. A tera of seconds. If we were to back up in history, a tera of seconds, it takes us to something like 1,000 years before the time of Jesus Christ. It's hard to visualize how big that number is. Okay, it's huge.
Is that metric in scientific notation what's shown at the top? Differences in M and N, or what is that? 1,000 M and then 10 M on the top.
That's just giving you the unit value based on 1,000, unit value based on 10. So you note the difference in decimal. That's 8 instead of 24 because they're 3 different. So that's power 10 versus power 1,000.
Power 1,000. Are they related by 3? Well, like 8 times 3 is 24, 7 times 3 is 21. 1, 6 times 3 is 18.
Right, well, and they're doing it because of the number of
The 3
groups.
zeros.
Right. So, Mr. Bauer. Okay. So yeah, I kind of like Yoda. Man, I got me a Yoda. I got me a Yoda of pennies. How much is a Yoda of pennies?
I don't think there's enough money on the board.
Well, that's going to be more than it's going to be 10 Zeta of dollars, right?
Yeah.
10 Zeta of dollars would be pretty darn good, right? Yeah, baby. Same thing here. What's a Yocto?
Oh,
That's small, right?
that's kind of quick.
Well, didn't we say a coulomb of electrons is 6.28 times 10 to the negative 20, or 10 to the 20, not negative, 6.28 times 10 to the 26? Well, that's pretty close. Okay? So Yocto is going to be 10 to the 24th. So Yocto is going to be, even a gaggle of coulombs, right? Even a few coulombs. That's a lot. That's a very small number. But when it comes to atoms, it's still a pretty big number, right? Pretty hard to visualize that.
Do we need to know that short scale, long scale?
I got nothing. I saw that, and that's part of the reason I grabbed it. I don't. I know the short scale. I've never heard of a millard, a billion, a billard, a trillion, a trillard, etc. I've heard of this one, and it's been in. I think I got that off of Wikipedia. So it is kind of interesting. They didn't invent some of these until the 90s. Okay, they just never had a need to count that high, right? I don't know about you, I'd get lost just making all those zeros. Okay, so you remember fractions and decimals are the same thing? A fraction is just a decimal is just a fraction with a 10-based denominator. So if we want to convert one value to the other value, to convert decimal into fraction, figure out what the denominator you want is. So let's say I make 2.375, and the denominator that I might want, let's say we could call it 16ths, or we could go with eighths. Well, what I'm going to do is I'm going to take the value after the decimal point and multiply it by the desired denominator. So if I take this value right here times, let's say, 8, what I'm going to come up with is 0.375 times 8 is going to end up being 3, and then I'll take the denominator and put it underneath it. If I'd used 16, that would have been 6, etc. So what do you do if it's some kind of weird number? So let's say this was a 7. Now I would have ended up with 3 point something, right? So I would have said 2 and 3 point something. Well, if it's small enough value and I'm building a fence, I'll just drop it off. On the other hand, if it's somewhere like maybe it's fairly close, let's say it was 3.5, right? Well, maybe I'll go back and go to 16 instead of 8, because that then would have turned this into 7. 7/16, that's on my ruler. So part of what you're going to pick for your denominator, if you get a value like this, is whatever's on your ruler, right? If I don't have 16ths, okay, I might get a different ruler. Ruler that only has 8s is pretty much worthless. Going the other direction, taking the 3/8, that's just a division problem. All I got to do is take 3 divided by 8, and that'll be the fractional component, put a decimal point there. Right? Now some of you might have one of them, their fancy micrometers where you just push the little button and it does it automatically for you. The downside of those is you don't know what their truncating or scientific notation rules are. So when it converts to fraction, from decimal to fraction, if it was 377, does it go to 3/8 or does it go to 7/16? Or at what point in here does it flip from being 3/8 to being 7/16 or 30 seconds or 64th or 1/28 or what degree does it take it down to?
Isn't that why we simplify?
Well, that would be one way of doing it, but if you've got a micrometer that's automatically doing that for you, you don't know what its rules are, right? Unless you play with it some. Okay, you guys remember all that? I know some of you are going, oh, I don't really want to remember that. Okay. So the other thing that's of use to us, sort of get to the end of this, is algebraic transposition. This is really, really useful for us. We can do things like derive pi r squared. It's been a while since I've done that one. I need to review it in my head. Pi r squared, what you end up with in deriving it, you take a circle and make a bunch of triangles and go all the way around. And then the number of triangles you've got, base times height, okay, but part of that value you don't know. The dimension at the base you don't entirely know because you keep adding more and more triangles. Keeping adding more and more triangles. Well, eventually one value becomes infinity on the inverse, and the other value becomes the number of triangles as infinity. So you have infinity divided by infinity, which becomes 1, so that disappears, and the only thing that's left is pi r squared. Well, that's kind of useful. Pi r squared, that's a useful number, it tells you, okay? I can substitute, I've already done it a bunch of times. In fact, we can substitute some values for power, current, voltage, and resistance and come up with two equations which we'll write on the board. There it is. And we'll use the little trick symbol here that tells us that times that equals that, this divided by that equals this, this divided by that equals that. That's one part of Ohm's law. Another part of it is going to be voltage divided by current equals resistance. Okay? I can swap any part of this with the other two parts of the other equation. So I can intermix these equations in a whole bunch of different ways and solve for every instance. So if we look at those two, we have 4 different symbols, right? P, E, I, and R. And for each symbol, there's 3 possible combinations that could go into it. So for P, I could have EI, I could have ER, or I could have IR, right? So we could then solve for each of these. So we would say P equals, in the first case, doesn't it equal I times E? Then in the next case, we can say, so we'll replace a few things. So we'll say P equals I, and then we'll plug what equals E? Isn't it I times R? So we can say I times R, or we can reduce that to I squared times R, right? Okay, then there's going to be a third value. So we've solved for PIE, we've solved for PIR. We now have to solve for PER. So we have to replace the E in this, we have to have E in the equation. So P, we'll use the commutative property equals E, and we'll replace the R, replace the I with ER, right? So we'll say E, and then we'll say times E divided by R. Okay? Now, can we reduce this? Well, one way to visualize, remember we can turn anything into a fraction? Let's turn that into a fraction. E over 1. That makes it a little easier to see, right? Multiply across, E times E is E squared. 1 times R is R. So eliminating all that will make this R and that E squared, right? So again, we reduce. So now we have the 3 instances of Ohm's law solving for P. What else? How about we solve for the instances of I? This can be a little confusing. So in one case, didn't we say it's P divided by E? Okay, P divided by E. Okay, we have also said that I equals E divided by R. That's another instance, right? We've not said that. So what's the third instance? We've had the combination of P and E, and we had the combination of E and R, but we haven't had the combination of P and R, right? So how are we going to solve for that? Well, let's see. So we want P and we want R. So let's use what we did up here and say I equals P divided by, and then we'll have to replace E with another representation. Doesn't E equals I divided by R? Okay, so we can say P divided by I times R equals I. So now I got I on both sides of the equation, and I'm trying to solve for I, right? So, what can I do?
You can move the IR over to the other side and times it. And that'll give you an I squared R.
Well, can I just do this? Multiply this times and this times I over 1? That's going to cancel the 2 i's here, right? And this is going to become I squared. So now I'm going to have I squared equals P over R, right? Then I can take the square root of both sides. Okay, because isn't that allowed? That doesn't change the equation. I take the square root of both sides. So the square root of this cancels out, and that becomes the square root. So that sort of becomes your formula right there. So that's your third instance of I. I stayed with the rules, right? I'm allowed to take the square root of both sides.
We could have figured that without that step, right? Because I could solve both P and R. So if you're combining the two, it shows 2 i's, I squared.
Well, but the problem is you don't know the I.
Okay.
You don't know what the I is here. So somehow you've got to get it out of this side because you got nothing to plug in. You're trying to solve for I here. So we had to get it out of the equation, out of this side of the equation because we don't know what it is. So we then went over here. We could have left I squared and done it that way, but at some point you're going to still have to hit that square root value. So if I did P divided by, I'm going to come up with a value that represents I squared. You're going to have to hit that square root anyways, right? Okay, so so we can erase that. We don't need that value. That was just part of it. So what else are we trying to solve for? Let's solve for E. So we've said E equals I times R, right? We can also say that E equals P divided by I, right? Just pull those right out of the formula and plug it in. So what's the third instance of E? We've got I and R covered for, we've got P and I covered for. So both states of I are covered for. Well, what else do we need? Don't we need P and R? So the solution for P and R is, and there's probably several different ways of doing this. The solution for P and R is, let's use the one where we've already got a P, and we're going to put the value replace this with something that has R in it, right? So we'll say we've still got the P, and then I equals E divided by R, right? E, let's do it. P divided by, what do you say? E R, right? We okay there? Now, the reason I did that is because I'm going to do that sneaky little rule that allows me to turn that into a fraction, right? Then I can turn this into multiplication if I reverse these two, right? I haven't changed the value of the equation, right? Now, if I multiply both sides of the equation by, not 3, E over 1 and E over 1, I should end up with E squared equals, these two cancel, right? So don't I just end up with P times R? PR, right? Then I take the square root of both sides, and I've now solved for that last instance of E, which ultimately is going to end up being E equals the square root of P R, equal them out over both of them. All right, and then same thing, the last one, for R, we have said, solving for the three instances of R, we have said that R equals E divided by I. Okay. So now we've got to get the other instances of P in there, right? We've got to solve for, so that it has P and E, and that it has P and I, right? So let's replace the E. We're going to say R equals divided by I. We're replacing the E, okay? So we're going to end up with sort of the same weird situation where it might be easier to go the other route and say I divided, might be easier to see it, I divided by P over I, right? You okay there? I've kept the equation good, right? Okay. Again, that's over 1. So let's flip the equation around. We're going to make this multiplication, change that into I over P. The end result is going to be I squared over P equals R, right? Guys still with me? All algebraic transposition. We've gotten 11 of the 12 possible formulas of Ohm's law. Equals I squared over P. So what's the last one? Is going to be R, and we solved it for I, so now we want to keep E. So it's E divided by, let's replace I with P divided by E, and it's gonna end up being the same problem, right? Isn't it just gonna end up being the same problem? So we're gonna be able to say E divided by P over I. We do our transposition again, and we should end up with E squared, R equals E squared over P, right? That should be backwards. Should be the other way around. No, I shouldn't have been replacing, in this one I should have been replacing the E, shouldn't I? I have I and P, I have I and E, I was looking for, so what I've replaced is the E. I've got the I here. I'm replacing the I with P divided by E, so that should have been E. That's what my problem was. Okay. And then when you resolve that, again, flip it, E squared under P, or over P. That somewhere in there should be, although it's not up here, that should be your chart of the different formulas, right? You remember that wheel that goes around? It's on the next PowerPoint. Alrighty. Then the last one, you guys remember the algebraic matrix, both from DC. Also, didn't we use this in general for weight and balance? Pretty sure you guys did, right?
Yes.
Technically, it's a form of a spreadsheet, although the advantage of a computer-based spreadsheet is you can define different variables in and throughout. Whereas using this sort of mathematically, what we're going to say is this divided by that equals that, this times that equals that, this times that equals that. So whatever that mathematical relationship is here translates all the way across. Whereas in a spreadsheet, I can make the rules different for each one. Okay? But for our intent and purposes, if we have a whole bunch of values and we want to kind of do the same math in each column, then the matrix allows us to do that and keep our data organized, right? We know that we only plug things with ohms in here, things with amps in here, things with volts in here, and things with watts in here. And then for each instance of a load or a resistance, we'll have different values. Now, do I have to do something different if it's a parallel circuit?
Possibly.
Something different like that.
Well, do I have to organize things differently when it's a parallel circuit?
No.
No, the math you may have to do is going to be a little bit different. But for each load, for each resistance, there will be a unique current, a unique power being consumed, a unique voltage drop. Now, in some cases, the voltage drop for each of them in a parallel path will be the same. So I might see some of the values repeated. But for each unique load, 1, 2, 3, 4, 5, there will be the other three ingredients included. All right, let's dive into a little bit of DC theory. Yeah, there's the wheel right there. It used W and E and so confusing. Yeah, I did have that.
R equals E squared.
You know what? I flipped that one backwards. I thought that one was off. Okay. So the properties of matter. We'll talk a little bit about matter, then we'll talk a little bit about energy. Guys probably remember there are atoms. Atoms is the smallest component, particle component, that will retain its unique characteristics as an element. Meaning it's the temperature at which it'll solidify, turn into a gas, liquefy, its ability to conduct current, its ability to insulate, its ability to be magnetized. All of these characteristics go away if we go to particles smaller than an atom. When we go to particles smaller than an atom, we end up with only 3 particles. Okay? Once you get to particles the size of an atom or bigger, then each atom will contain some unique characteristics. However, there's only, whatever it is, 100 or so unique types of atoms possible. I don't think it's quite 100, but all right. Each type of atom will have a unique set of characteristics. However, they often will share characteristics across the board. So there are many atoms that will, above a certain temperature, above some range of temperatures, will turn into a gaseous state. There's a whole group of atoms that love to conduct electricity. Okay? There's another whole group of atoms that like to form in crystalline structures. Okay? But no single atom of one type of element will be exactly the same in every characteristic as another type of element. And one other thing, so an element can be composed of a bunch of atoms, or there are a few types of atoms. They don't like to play with anybody else. They don't like to play with their own like fellows, the same kind of atoms. They don't like to play with any other kind of atoms. They just want to be left alone. They are like total, what was the guy's name? Bundy, Ted Bundy? You know? Don't like nobody, anybody at all. They just want to be left alone. Most atoms, on the other hand, do like to play with another atom. They'll either play with a whole bunch of atoms, or they'll play with another atom of the same type, or they'll play with atoms of other types of atoms. Okay? But anytime 2 atoms get together or more, we call it a molecule, and they chemically interact and connect through one of the properties of chemistry. If I take an atom here and an atom there and set them next to each other and no chemical reaction occurs, they're just sitting there on a bench, not doing anything. Okay, they're still two different elements. Once they attach, like oxygen, let's say 2 oxygen molecules, they come together and they usually, almost always, will share an electron or 2. So an electron that's traveling around one will start traveling around all of the atoms in that molecule. If I have 2 atoms of different elements, it becomes a compound. So if I mix a little bit of oxygen and a little bit of hydrogen, and I allow for a chemical reaction, which in this case will release some energy, the end result will be a compound. Whereas the 2 oxygens together in the O2 state, that's still an element. Okay. Anytime an atom combines or separate, or excuse me, anytime atoms combine into a molecule or separate out from a molecule, there will be a change in the state of energy. Now, sometimes it's combining that releases the energy, sometimes it's separating that releases the energy. Depends on the chemical relationship. So for oxygen and hydrogen, we have to add a fair amount of energy in to get the 2 hydrogen atoms to leave the oxygen molecule. If they come back together and chemically interact, they will release that energy. Okay, so we could say that the free oxygen molecule and the 2 free hydrogen molecules are at a higher state of energy than when they combine and become a water molecule and release some of that energy. Okay? And we know what the release of energy looked an awful lot like, right? Big fireball, called it the Hindenburg. Actually, the truth is, the release of energy in the hydrogen burning, no one ever saw it. It didn't show up on film. Hydrogen burning usually doesn't emit any light. Okay. Also, none of the hydrogen burned in the airplane, in the blimp or the Zeppelin. There was a spark that started the reaction, immediately ruptured the bag, and all the hydrogen shot upwards. Okay. Of course, it was burning, but clear burning, no light being emitted, and it got the bag burning. The bag was made out of linen covered with nitrate dope or primer cord. Okay, really, really, really flammable. I mean, as flammable as gasoline flammable stuff. So it all started burning. That's what all the flaming was. And all that flaming material came down and landed on everybody, burned them all up. Actually, the people in the gondola, there were a number of people surviving in the gondola. They got broken bones and everything because it dropped, whatever, 70 feet or something like that. But being in the gondola, they were protected from all of that burning material falling on them. Then, on top of all that hydrogen that went into the atmosphere and was releasing heat energy and combining with oxygen, it formed enough water to precipitate a cloud and rain. So it started raining in and around the Hindenburg. Sort of kind of a rude irony, burned you all up and then doused it with rain. Right? It's kind of like out of a Wile E. Coyote cartoon, the Roadrunner. It was interesting. We stopped using hydrogen, but it took us a long time to stop using that nitrate covered either cotton or linen. Dangerous stuff. Okay, so oftentimes to get a chemical reaction to start, you have to add energy in because the current state of energy isn't enough. So like, for example, with hydrogen and oxygen at ambient temperature, if you had some hydrogen and oxygen, nothing would happen. If I increased the pressure or heated things up, there'll be some point where a chemical reaction begins to occur. And of course, as it does, it releases heat energy, which then warms up the environment and causes the chemical reaction to occur even faster. Okay, so we've got three particles we get to play with: neutrons, protons, and electrons. Neutrons and protons are essentially the same size. They're about 1,830 times bigger than the electron in terms of mass. Way, way bigger. As a result, they have a tendency to collect into the core and sit in the core, and they don't like leaving each other. They're pretty much going to hang out. So if you kind of want to do the Harry Potter thing and change an atom from straw into gold, well, I'm getting my stories mixed up, but anyways, you're going to have to put a whole lot of energy into breaking that nucleus up. In all likelihood, what's going to happen is as that nucleus breaks up, it's going to break up a bunch of other nuclei, and you're going to have what's called either a fission or fusion reaction, and you're going to be vaporized. And that's going to be a hydrogen bomb. It's very hard to make that happen. In fact, to get it to happen, we have to super compress matter to get that kind of a reaction. We completely contain, to get a fission reaction, we contain very dense radioactive material, uranium, in a shell full of highly explosive material that's designed to compress inwards. At a certain point, that material will start to have this chain reaction where the nuclei start to disintegrate. And then, of course, rapidly blow other nuclei apart. To get a fusion reaction going, we will take some hydrogen or other material inside the fission reaction and compress it down to get the hydrogen bomb as opposed to the atom bomb. And it'll make an even much bigger bang. Okay, but of importance to us is the electron is really little, and it doesn't really like the protons. So it tries to get away. Only the proton and the electron sort of have a leash attaching them to each other. There's this force called electrostatic force connecting the two, keeping them sort of tethered together. The electron also is incited, and I don't know that we know why, but it likes to spin around the core of the atom. So it spins around at the speed of light. In fact, electrons don't do anything else but travel at the speed of light. They really, really like going 186,000 miles per hour, or 300,000 meters per second. They can, however, be convinced to move from one atom to the next if we've got the right kind of atom. A part of what happens is these electrons don't like each other, so as they're going around, they avoid each other. Really, really avoid each other. They avoid each other so much that they'll sit in this little orbit, and if I add another one, these two say, yeah, no, you got to go to the next orbit out. So the other one's kind of out there, and any more I throw in, pretty soon that next orbit or shell gets filled up, and they say, yeah, no more. And of course, to get an electron to stay there, I'm going to have to add another proton and another neutron. Now, the one exception to this is the smallest atom doesn't actually have a neutron. That's hydrogen. It's just got a proton and an electron. All other atoms, it's the same number of neutrons, same number of protons, and can have the same number of electrons, or they might be missing one or have an extra one, depending on the nature of the atom. So while truly, for example, helium, you've got two atoms or electrons buzzing around like this. The orbits are a little random, so as they change and they're going the speed of the light and they're infinitesimally small, it ends up forming what looks like a shell. Now, if I have a full shell, like 8 electrons or 18 electrons, then all these guys trying to avoid each other, they definitely form what looks like a shell. And then as they fill up, another shell and another shell. And there are some rules around that. Probably what matters to us more than anything else is the state of how full the shell is. Okay. Beyond that, we're not too worried about the chemistry. We're only worried about the behavior of the electrons, not the chemical behavior of anything else. So it turns out that if I have an atom where all of these guys are full, all of these guys are full, all of these guys are full, and there's one lonely electron sitting out there going, come on guys, let me in, let me in. They're like, nope, not going to happen. So that little electron's out there bebopping around. It's like, well, fine, I don't need to play with you. I'm going to go somewhere else. So it departs and goes somewhere else, finds another. Well, what's probably next to that copper atom? Another copper atom, right? Okay. So it's going to go to the next copper atom. And depending on what's being motivating things, as it goes to the next copper atom, the electron on that copper atom says, hey, wait, what are you doing over here? I'm going somewhere else. So they start bouncing around. Another situation is I could have my outer shell only half full. Well, if I do that, what's going to happen is, first off, the material is going to try and keep some of the atoms full by sharing. So it'll form a very crystalline, structured arrangement. But a fair number of the shells on the outer edge of that crystalline structure are only going to be half full. So we could convince them, if we intermix a few other kinds of atoms in there, we could convince them to take on an electron or not take on an electron, depending on what we're doing. Okay? So this would be a good conductor or a good insulator, depending on how we bias it. So we're going to call it a semiconductor. Out on the other end of the spectrum, something that really doesn't like to conduct electrons is something that has a full outer shell. Okay? That's cool. A perfect insulator. You will not get electricity to travel. Perfect insulator. The problem is, the outer shell's full. It won't chemically interact with anything either. It doesn't like it just doesn't, it's a hermit. Doesn't like anybody. So you can't get it to form into a solid. You can't get it to form into a liquid. It doesn't like anybody. So it's really hard if you want to use it as an insulator to wrap it around something. About the only thing you can do is put it inside something. So, for example, we want to create a field where we can conduct a fair amount of electrons through. We can put it inside something. We can put a gas in there that doesn't play. So, for example, you guys remember the old vacuum tube, right? Actually, more often than not, these were not filled with vacuum or nothing. That's a real pain in the butt to get all the molecules out of here. Much easier. It also causes it to structurally be stressed because of pressure on it all the time, and it can leak. But much easier, fill it full of this gas that doesn't like to play with anybody. In fact, those gases, we call them inert gases. They are inert. They don't chemically react, they don't do anything. However, I can bring this up to about the same as atmospheric pressure with, in this case, argon. Okay? And so there's no stress on this. It's not likely to leak. And the electrical interactions that are occurring in here based upon a certain amount of radiation that's formed from electrostatic force won't be affected by the gas that's in there. Okay? It won't start trying to conduct because of the gas. The energy will conduct for other reasons, but it won't be because of the gas that's in there. All right.
So noble gases are used a lot in lighting. Or
What?
Noble gases, like, cause they have some in neon light.
Yep. So they are often used in lighting because they will take a charge, but they resist it so much that they will emanate a fairly large number of energy packets called photons when they're charged. And it takes a lot of voltage to make it happen, though. Okay. But they themselves won't chemically interact. They'll do everything in the power to get rid of that extra electron by emitting a fair amount of energy. And then they'll go around, go about their business being a hermit until they get charged again. So these guys that are full valence shells or inert or noble gases, they don't make good insulators because you can't get them to stay in place. So it's also typical that when atoms combine, they not only do they share electrons, but they often become polarized. So for example, an oxygen molecule, it's a pretty big molecule, or oxygen atom. It's got 8 protons, 8 neutrons, 8 electrons, and it attaches to 2 hydrogen atoms, which have no neutron, 1 proton, and 1 electron. What's going to happen is those 2 hydrogen atoms are going to attach, and they're going to kind of sit a certain distance apart from each other because the 2 electrons are going to get robbed, and they're going to sit over there sort of mostly bebopping around the oxygen atom. So that means the protons sitting there in the hydrogen atoms are going to be kind of positive. So they'll push away from each other a little bit, but that side of the atom, or the molecule now, will be somewhat positive charged, and the oxygen side of it will be somewhat negative charged. That means when it then goes to interact with other like molecules, they'll all form into a nice lattice work. And in a liquid state, you've seen how water behaves. And in a solid state, they actually have to change their structure a little bit. That's why water is one of the few elements that goes solid. The way the atoms all line up, the molecules all line up, expand a little bit. That's why it gets a little bit bigger when it freezes. It goes into the solid state. Okay. The other thing that can happen is when you combine these different atoms together into different molecules, different characteristics occur. Sometimes it will be a good insulator. Sometimes it will be a better conductor. Sometimes it will be able to conduct magnetism better, and other times it will resist or interfere with the flow of magnetism. So, and some of this is, it's just, it's fact we figured out. We don't necessarily completely understand why. So, again, atoms with 1 outer shell are your best conductors with 1 electron in the outer shell. It's also not too bad if it's got 1 hole. So if I've got a shell that's almost completely full, that'll take on an electron. And then when another one comes along, it'll give it up and take the next one, and the next one, and the next one, etc. So that makes an okay conductor as well. If we can take a semiconductor, yeah, there's your noble gases. We can take a semiconductor like carbon, sorta, silicon better, and then we intermix some other types of atoms in there that have either one extra electron or one extra hole, and we intersperse them, we can convince that structure to either, by charging it a little bit, if we forward charge it, it will conduct electricity. If we reverse charge it, it will actually resist the flow of electricity. So we can cause the semiconductor to become either a good conductor or a good insulator, depending on how we bias two different sets of material. So we'll take silica with one material and silica with another material. So one material will have extra electrons, one material will have extra holes, and we bring them together. Now these guys figured this out. Not only figured it out, but they figured out how to take a bunch of silica and put a bunch of little atoms in there called doping. This was back in World War II that they figured this out. Man, they still had horses drawing carriages around, you know. So, as we get into, I'm going to stop here, but as we get into particle behavior, we have to start talking about the forces that they exert upon each other. In this particular case, these forces are going to be an electrostatic force. And the force, by the way, is a function of physical force. It's literally, they are pushing against each other, repelling, trying to avoid each other, get away from each other, or they're pulling towards each other. It's physical force. So the electrons are trying to push away from other electrons. And they're trying to pull towards other protons. The protons don't like each other either. Now what's interesting is the protons don't like each other, but how do they clump together? Well, remember, the proton, the amount of energy between an electron and a proton is pretty significant. However, the proton is 1,830 times bigger, more mass. So the force of gravity, as well as the force of gravity coming from light protons, but also the force of gravity from the neutrons, is stronger than the static force for those much larger masses. Well, they stay clumped together because of gravitational force. And gravitational force is the one force that always attracts. It never repels. So the protons and the neutrons are forced to clump together into a core. But the super light electron, it's like, I'm going to speed of light. I don't need you, but oh, wait a minute. You're keeping me close by. So all I can do is spin around. Okay. Not only can I spin around, but as a particle, I'm also orbiting. So I'm orbiting and I'm spinning, doing both. And that motion of the electron, both spinning and orbiting, directly causes a magnetic field or magnetic force. Okay, the magnetic force will be at right angles. So the magnetic force will be this direction versus the direction towards the static force towards the center of the core. So magnetic force is always at right angles. It's also at right angles to the direction of travel. So if the electron's traveling this way, the magnetic force will be at right angles to that and at right angles to the static force, pulling down. Okay. Neutrons, they don't have a static or magnetic. There's nothing. They got gravitational force though. Now, again, I'm going to, before we move on, I will take our break, but I want to just sort of put it in your mind how small these guys are. They're really little. So if you take a metal pin, just a little metal pin that you stab yourself with, not the big T-pin or the kind with the big plastic ball on it, just the one with the little bitty small head on it. So you cut that little head off, and you take all the atoms in that little head, and you make every one of them the size of a grain of sand. Okay? The amount of sand you have would fill all the oceans and cover the earth 600 feet deep in sand.
In one half.
No, in one tip. of-
In the tip, in that one little head, all the atoms
All the
that are contained in that one little bitty speck of metal. Okay? There's no other way I know how to sort of visualize how many atoms there are.
Compact it is.
They're little dinky bitty, itsy bitty things. So the idea that we have come up with this thing called an electron microscope and actually taken a picture of an atom. We actually did this long, long ago before many of you were born. To me, that's pretty amazing, given how small they are. All right, let's, I ran a little over, so let's come back at 25 till 7.